So this is a question. A uniform cube of mass m and side length a is placed at rest at the edge of a table with half of the cube overhanging from the table. The cube begins to roll off the edge as shown in the diagram. You can see that. There is sufficient friction at the edge so that the cube does not slip at the edge of the table. We need to find the angle theta through which the cube rotates before it leaves contact with the table, and we need to find out the speed of the center of the cube at the instant it breaks off the table. And the third part is the rotational kinetic energy of the cube at the instant its face AB becomes horizontal. Students, new students who are new to this problem, I say them put a pause, try for it, then you can check the solutions for it. So let me go to the solution part of this problem. So as you can see, we need the cube is rotating about this point P. So we need to find out the moment of inertia of cube about rotation axis passing through point P lying in the face of the cube. We know that the moment of inertia of the cube about the center of mass about an axis perpendicular to the plane of the cube is ma square by 6, but we want the moment of inertia about point P. So using parallel axis theorem, ma square by 6 is the moment of inertia about its center of mass plus m into perpendicular distance square, and by solving this we get to be 5 ma square by 12. Now the cube, as it is rotating about point P, the rotational kinetic energy of the cube is gained due to the loss of potential energy when the cube is rotating by an angle theta. So as you can see, as this angle is theta, so of course this angle will also be theta. So what will be the loss in potential energy when the cube rotates by an angle theta is nothing but mg into we can say this is the height it loses, so delta h, so a by 2 minus a by 2 cos theta is the loss in potential energy. First one is a by 2, now it is a by 2 cos theta, so you can see this distance is a by 2 here. So initial potential energy of the cube is mg into a by 2, and now the potential energy is this length will be a by 2 cos theta. So loss in potential energy will be mg into a by 2 minus mg into a by 2 cos theta. So I took mg into a by 2 as common, so we get it to be mg into a by 2 into 1 minus cos theta. So this loss in potential energy will be equal to rotational kinetic energy, that is nothing but half I omega square. I already we got it to be 5 ma square by 12. So by solving this, I find out m omega square into a is 12 by 5 mg into 1 minus cos theta. I keep it like this. And omega, I have shown it how the cube will be rotating in the clockwise direction, and what are the forces acting on this cube I have already shown it, that is mg, and one is normal reaction. So as it's asking the angle theta through which the cube rotates before it leaves contact with the table, we know that when it leaves contact with the table, the normal reaction will be 0. So as if you can see, I have given here, if the cube loses contact, then normal force N is equal to 0. So here we can say what are the, if I write this equation over here, that is mg cos theta minus normal reaction is nothing but centripetal force, that is m omega square into radius through which the center of mass is rotating is m omega square a by 2. So here what I did it, n is 0, so you can see here n is becoming 0, so I take it to the next board, that is mg cos theta must be equals to m omega square a by 2. I put it to be equation 2, and m omega square a by 2 already I can write down here. We can write down here as m omega square a by 2 will be nothing but by 2 becomes 6 by 5 mg into 1 minus cos theta. I can keep it like this. So here mg cos theta is equal to 6 mg by 5 into 1 minus cos theta. By solving this equations, I can get it cos theta naught, which I said that theta naught is the angle through which the cube leaves at that point, is nothing but 6 by 11. And I can put this cos theta naught in equation 2 and to find out the value of omega square. Now as we can see here, velocity of the center of mass, here we can say here velocity of the center of mass is here, this is the velocity of the center of mass. So velocity of the center about the point P, the perpendicular distance is a by 2. So I can say here velocity of center of mass will be a by 2 into omega. So by solving these values, I can put it over here. We get it to be 3 by 11 into Ga root over. Now next point, many students here do mistake, rotational kinetic energy. Now once it leaves, the cube leaves, so the cube will be rotating about its center of mass. Now it will not rotate about point P because it has left the point P, but it will be rotating with the same omega at the instant of leaving point P. I have assumed that the angular speed of the cube is omega. So it will be rotating with omega, but when I take the rotational kinetic energy, I will take it will be half into I moment of inertia about its center of mass. Don't use moment of inertia about point P, because now it has left point P. The whole cube will be rotating about its center of mass, but with the same angular speed as it left the point P. So moment of inertia of the cube about its center of mass is ma square by 6. So half into ma square by 6 into omega square, already we got it. We get it to be mga by 11. So hope you like the solution. So we'll be going into the next segment of another advanced problem of rotational mechanics in the next class. Thank you.